to start with, I just want to ask, like, raise your hand if you've done some web programming in your lives. Okay, so this is going to be awkward because I haven't, more or less. And nonetheless, I'm more or less going to give you a talk about an approach that we're thinking about and working through and starting to develop about how to do web programming, and specifically how to do web programming in OCaml in a way that really kind of aligns with kind of functional ways of thinking. And some of the experience I have is from kind of thinking about it myself, and some of it comes from talking to people who've worked on other kind of approaches to web development out there. Like, I've talked a lot to Jordan Walk, who's the guy who did React, and to Evan Ksaplicki, or whatever his last name is, who did Elm, which is another programming language for doing web applications. And a bunch of work with people internally who know more about web applications than I do. So this is going to be a short talk, so I'm really only going to be able to give you a little bit of a flavor of it. And I'm going to try and walk you through the basic ideas and some of the kind of interesting technical problems that come out of it. So feel free to like jump in and ask questions. Or I guess, are we waiting for questions till the end? You can do that too. But it's really going to be just kind of a little bit of skimming over the surface to give you a rough feel for the approach we've been taking. Okay, so what? And so the title, Building Reactive Web Applications Without Really Trying. The point about this is it turns out that in some ways, building web applications, and I mean web applications that run in a web browser, like things that are kind of JavaScript enabled that react directly to your own interactions, not just things that like web applications that go all the way to the server every time you need to do anything. That's the kind of application we're thinking about. And it turns out that taking a bunch of pre-existing ideas and concepts and just kind of slamming them together, we're able to get much farther than I would have naively expected. So the starting point that I ended up picking is the Elm architecture. So the Elm architecture is like a particular design idiom that was put together for the language Elm by this guy Evan, and this sort of came out of the research that he did as an undergraduate at Harvard when he was kind of studying PL stuff and working with a guy named Greg Morissette, who's a very well-known guy in the PL community. So he came up with some nice ideas about how to express a functional way of expressing user interfaces. And that way can kind of be boiled down in some sense to a simple signature. So I'm going to kind of pop back and forth between slides and Emacs. Raise your hand if you've read OCaml before. Woohoo, that's a lot. Haskell? Okay, raise your hand if you've never used a statically typed functional language. Okay. All right, so please ask questions if you're lost in anything, but I'm going to go with the assumption that the syntax is not like completely foreign to the people here. So the basic structure that the Elm architecture shoots for is pretty simple. So you break up your application into three pieces: a model, a view, and like a thing that's hard to talk about that ties the two together, right? People talk about like model view controller UIs, and there's lots of different things people mean by that. So this, in some sense, is model view and something to tie them together, and that something is maybe a little different from what you're used to from seeing, say, an object-oriented model view controller style design. So the model, in some sense, is very simple. It's just some type, a pure type. So we're talking about some value that is not modified ever modified by mutation, and we have another type called the action, and you can think of the action as a function from model to model, right? It's like a packaged up thing that transforms the model from one state to another. And typical actions might be, you might have an action that comes from when a key is pressed or something is clicked or something like that. Something that you kick off an action which causes your view of the world, your view of the state of the user interface to change. And that might be from user activity, it might be from network activity. And then you have this last function called the view. And the idea is the view is itself just a function. It has two arguments, the model, which is just like the current state of the world, and the second one, which is like a function for scheduling actions. And this is used for essentially embedding callbacks into the view, so that when someone presses a key or clicks on something, you know what to do. You basically hook in a callback which will schedule that action to be taken care of, to be applied to the model in the future. And then this returns what's called virtual DOM. And for the moment, you can just think of this as an abstract representation of what do you want the DOM tree in the browser to look like. Ooh, important question. Raise your hand if you know what the DOM is. Excellent. Okay, so I'm not going to talk too much about the DOM, but maybe those of you who dealt with it know that programming directly against the DOM can be kind of awkward. Changing the DOM is itself expensive, and it's like a big mutable data structure. So figuring out how to both like set it up from the beginning and then update it when things change can be a little bit of an awkward programming exercise. So the idea of the Elm, this Elm architecture is it gives you a fairly simple way, kind of almost too simple to be taken seriously, of like tying these two together. We just have like a model that tells us what the state of the world is, a view which is just a simple, pure function that generates a description of the UI, and this action type which is used to tie those two things together. Okay, so do anyone have any basic questions about like what this means and what it's about? Okay, so it's worth saying that I'm calling this the Elm architecture. There's something relatively similar that's going on in the React framework, which is another JavaScript framework, and there are lots of places where these basic ideas show up. But Elm is does a good job of packaging it up in a really clean and easy to understand way, which is why I started there. So the basic insight, I think, of that all this is based on is that the Elm architecture is actually a really nice way of expressing user interfaces. If you sit down and try and write a user interface this way, it's actually not that painful to do. It comes out relatively nicely. The problem is not figuring out how to express how your UI should behave. The problem is making it perform. Right? So if you think about, I mean, just go back and think about like this thing I described, you might wonder like how the hell this will like work adequately well if I am building a complicated UI with lots of things in it, right? Like, really, I'm going to like generate this new complete copy of the view every time anything, like every time someone clicks a key, I regenerate everything and I slam it all onto the screen. Like, it sounds ridiculous, and in some sense it is. And so the real question about the Elm architecture is not once you have it, how do you program with it, but how do you make it not a dog, right? How do you make it perform reasonably well? So there's a few approaches that people have taken to this. The ones that you see in most places are all organized around this idea of virtual DOM. And as I said, virtual DOM is just like a pure data type that represents what you want to end up on the screen, what you want the DOM to look like. And there are two optimization tricks that people do. Trick number one is that people use diffing techniques to minimize the amount of changes you have to make to the real DOM. So this all comes from the mental model that touching the DOM is like super duper crazy expensive and everything else doesn't matter. So don't worry about the fact you have to create the VDOM over and over. Just like diff the new VDOM against the old, there's simple functional data structures, so you can do that efficiently. And then you only have to apply the actual changes, and those are typically small. And so you can kind of do the optimal thing because you have all the data in front of you, so you can have a clever algorithm that figures out how to minimize the diff effectively. So you can do something really nice in terms of updating the DOM, and there you are. And for small applications, this story is actually enough, but it's also kind of obviously ridiculous in that you can't imagine scaling to really big displays and somehow having all this work. So that's not the only story they have. The other story is that they use some form of memoization, basically remembering the results of previous computations to avoid having to regenerate the VDOM in its entirety every time. And if you go to the webpage of Elm or React and sort of look at how they describe the world, they always describe the world in terms of the first bullet, because the first bullet is pretty. And the second bullet is kind of a pile of weird hacks that work pretty well, but are kind of complicated. And so they don't talk about that as much. And I'm going to talk a little bit about the second bullet and kind of how they approach it and how we can do better. So to say it's another quick picture thinking about what it means to make it fast, I want to kind of write down, and what does every good functional programming talk have? It's a commuting diagram. Not that much of the room got that. It's clearly a less annoyingly academic room than usual. So the idea is the arrows here are kind of describing the kind of flow of data that you get in an application like this. So on the left, we have the model. And you can think of the top row as the initial state of the program and the bottom row as the subsequent state. So the arrow from model to model is really the application of an action. Okay? And if you do the simplest possible thing, then, well, you have your model, you construct your VDOM, let's say it's the first time we did it, so we just slam the entirety of the VDOM into the DOM. And then the next time you apply the action, you recompute the VDOM, and then you compute the diff between the new VDOM and the old VDOM, and then you only apply the changes to the new VDOM. Right? And the thing to observe here is that some of these edges are kind of more expensive than others. I've marked kind of the light arrows as the ones that you expect to be the cheap operations, and the heavy arrows as the expensive ones. Right? And why are they, like all the things that you sort of think of have to be kind of all at once from scratch computations, those are the heavy arrows. And the ones that you feel like in principle could be small because the change is typically going to be small, those are the light arrows. And the problem we have with the simplest implementation of all this is that we cross too many heavy arrows. So VDOM, the VDOM diffing addresses straightforwardly those two arrows on the right-hand side, those orange arrows. And that the one at the bottom, you don't actually have to do typically, right? You can instead compute the arrow from the old VDOM to the new VDOM, and that lets you do this kind of parallel transport. You can compute what the transformation on the DOM should be based on what change happened to the VDOM, right? So far, so good? So that's one heavy arrow, but we still have this other annoying heavy arrow, right? Which is the arrow from the model to the VDOM. And that's the one that they attempt to attack these purple arrows by use of memoization. And the memoization trick is relatively simple. So the idea is these frameworks let you construct what are called lazy virtual DOM nodes. And the idea of a lazy virtual DOM node is you say, instead of constructing this node right now, what I'm going to do is I'm going to write down the inputs to that node and the view function that will like actually construct that. And I'll kind of package those up, and I won't immediately run the function. I'll just have this package that knows enough to compute what's there. And then, well, when do you decide whether you need to run the function? Well, in the process of computing the diff between an old virtual DOM and a new virtual DOM, when you're comparing two nodes to each other, you say, wait a second. Before I actually run down and compare them, first let me check, are these lazy nodes? Oh, look, they're lazy nodes. If they're lazy nodes, you say, oh, do they have the same render function, and do they have the same inputs? And if they do, you can just stop, right? So it gives you a way of shortcutting the computation of the whole tree. You don't have to compute everything at once. You get to stop the computation of these lazy nodes. And it lets you force the computation only as necessary in the process of computing the diff. Okay? Does that roughly make sense to people? Shoot. That's a good point. So this is actually one of the downsides of this approach, which is, I should go back a slide. So one of there are two basic downsides here. Downside number one is this ties your hands in terms of the ordinary kind of functional programming you can do. Because really the only reasonable comparison you can do on the functions is make sure they are physically the same function pointer. Right? So your ordinary way of programming within functional language, I'm going to have closures and higher order things. It's like you and your higher order functions can go to hell. Like they cannot be used in this context. So that's problem number one. You can't memoize on higher order functions. And indeed, you need to provide equality testing functions for the ordinary data as well. And that data also has to be kind of first order stuff. You can't just like put functions in the middle of that data either. So that's one downside. And then the other downside is the kind of memoization that you can do, the way in which you can make your computation lazy is concretely tied to the structure of the virtual DOM you're generating, right? So for example, if what you have is like a big table of users, right? And sometimes new information comes in about this user or that user and just affects the little sub piece about that user. This is great, right? Because most of the things don't change, the diff discovers that, everything's fine. If, on the other hand, you have a sorted view where you can change what the sort order is, and now like new entries are coming in and changing and keys are changing incrementally, you're dead, right? These approaches just don't help you at all, right? So it's very limited. There are certain kinds of things it does very well, but it's also quite limited in what it can do. Okay, so we came to think of this as a problem of incremental computation, right? If you think about this like commuting diagram I had up before, like what's really going on is I computed the virtual DOM before, And now it changed a little bit, and now I need to compute it again, right? So this is kind of a classic online programming problem, right? I want a program that can compute the value that I want, and then can update that computation as some of the inputs change. And this turns out to be a very well-studied problem for which there are lots of good solutions. And in fact, we have our own library called Incremental, which is aimed to solve exactly this problem. So like, screw their weirdo special case memoization nonsense. We can use a general purpose framework for solving this problem, and maybe that'll be all we need. So let me now quickly show you the interface of Incremental. So this is a simplified version of the API. It doesn't have all of the different pieces that you need, but just to give you a quick sense. So Incremental has three kinds of nodes. There are variables. That's the second one. Those are the inputs to the computation. There are incrementals themselves. That's the kind of interior tissue of the computation that you're building up. And there are observers. That's where you get output out of the system. And the key thing that Incremental is doing is it's structuring your computation as a graph, right, with sources and sinks and nodes that connect them all together. And the graph is actually dynamic, which is to say the graph can change in the course of the computation. And if you look at the little operators you have, these operators give you ways of building up new computations from ones you already have. So you can create new variables. That's what that var.create function does. You can watch a variable to get the corresponding incremental. And then when you have incrementals, you can use functions like map. And map lets you like transform an incremental. And you can use functions like both to take things from two incrementals and like merge them together. And you can use functions like bind to actually make dynamic choices about the graph. If you don't know why bind gives you dynamic choices, it's maybe not worth going into, but this is what's called a monadic structure, and you start with the map-like bit, and then when you add bind, you get a bunch of extra expressive power. And in this case, the extra expressive power is dynamism. And dynamism lets you do things like, I was computing this page, and then something happened, and now I'm computing a different page. Right, so dynamism actually matters a lot to this story. Sorry, did you have a question, Nicola?
Yeah, I think, aren't you missing something to set a variable?
Yeah, I suppose. This is the advantage of doing your slides in Emacs. Right, so it's worth noting that the interior computation is very functional in nature. Right, if you look at what you're doing when you're doing, the incremental map or bind or things like that, that all just feels like ordinary functional programming. Variables are imperative, right? You set the input to a variable, and observers are too. Observers are things that like give you callbacks, so you get to kind of read the value back when things have changed. Okay, so I don't want to go too much into detail on incremental, but the idea is it's this kind of combinator language that lets you build up these big graph-oriented computations with the idea that they recompute efficiently when the inputs change. Okay, does that roughly make sense? All right, so now let's go back to the slides, and let's see how incremental is going to save us and cause all our problems to go away. So remember, we needed in the end a function with one input and one output, so it's in some sense quite simple. And you have the model on the right-hand side and the virtual DOM on the left, and you want to efficiently recompute it when things change. So you imagine there's some like graph connecting the input to the output value, the variable to the observer. And then whenever the model gets changed, some part of the graph refires. So we made a change to the model, that's now dirty. All of its children have to fire. Then there's a notion of what we call cutoffs, where it might just, imagine model is like a 3-element record, and you like projected out the 3 different fields. Well, the 2 of them might not have changed at all, so those will cut off, but the other one maybe did really change, and so you have to continue propagating through the graph to refire all the parts of the computation that might have needed to be modified because of the change on the input. Right, so yay, incremental solves all our problems, sort of. So let's talk about, I want to kind of run through, how much time do I have? 5 more minutes? Oh, I'm totally hosed. Let me try and do a couple quick examples to highlight. I want to do basically one example to highlight how it kind of works, and one example to highlight why it's a disaster. So So this is like a really stupid, simple piece of view code. So imagine the top record here is just a record describing what you know about a machine in a data center. Okay, so it's like, it's got a name, it's got some internet address, it's got a load average and uptime, blah, blah, blah. And then I have this function view. And here I've done this kind of the original like Elmish way, where there's no incremental involved. I just, write some OCaml code that like pulls data out of the model and constructs the view and calls node.tr and node.td, and you can use some fancy syntax if you like having angle brackets in your source code, but like you basically just construct this virtual version of the HTML, and it's pretty straightforward. Okay? And then we can do, well, what if we wanted the incremental version of this? How's that going to look? And the answer is not especially different. Right? So the code looks kind of almost the same. There's a few like magic operators, let %map. So this is like a little bit of syntactic magic, which inserts basically the appropriate map operators, and it does them in parallel, so I can like get the values from a bunch of different incrementals. So like this code will run whenever any of these change. And I have some other tricks in here to kind of, again, grab the individual pieces and convert them to strings and try and minimize what has to get refired from the graph, so that when some of the inputs change and some don't, I don't have to recompute everything. So this looks nice, and it uses incremental in a natural way, but it's also kind of trivial in that, yes, I've put some incrementality into here, but the thing being constructed is so tiny that it's actually kind of boring. Right? Nothing actually interesting has occurred, right? I'm not really going to save enough computation to be worth all of this overhead. When do things like this matter? Well, they matter when you have big data structures. So imagine like I have, my overall model isn't just one simple machine. I have a big collection of different machines that I'm working with, right? So there's like a functional data structure, like a map. Right? And in that map, I have all of the different data things change. And now what the hell do I do? Right? Like suddenly this whole structure that I had in mind before doesn't work, right? It's like there was the model and it had like 3 static things I was getting out of it. Like, no, that's not the right picture anymore. Now the picture is I have a model and there's a dynamically changing set of outputs, right? And when one of them changes, maybe there's 1,000 machines I'm tracking that I want a view of. When one of them changes, like let's say the model changes, but really something was changed about just one machine, I really want to just fire the part of the graph that's due to that machine. And there's more things that can happen than that, right? Another thing changes that things can go away. I can have things drop out of my model, and then new things can get added back in later. So one of the things we discovered when taking this approach and trying to apply it to real-world problems is that the primitives that we had in this incremental library that we were using weren't strong enough. We needed more dynamism than we could get otherwise. And an interesting part of the story is that we actually added a bunch of new primitives into incremental to help us handle this kind of case. And it turns out the key part of the solution to this is the same thing that virtual DOM does, which is diffing. Right? The key thing you need to do to efficiently handle this case is you need to take your functional data structure, the model that is now and the model that you had before, and figure out what's changed about it. So you can just propagate the appropriate changes. And that ends up to be what we did to make this work. And you find this interesting structure as you build these applications is that diff and patch shows up again and again in the architecture. So we have like diff and patch at the very end of the story for figuring out how to propagate changes from the virtual DOM to the DOM. You have diff and patch as a way of making the incremental computations work efficiently. And then if you step back to the server and you want to think about how you efficiently transmit information from the server on, you actually want to do the same thing again, right? In fact, sometimes the server itself will also be built using incremental, and then it generates some output. And you don't want to send the whole thing over the wire. That would be insane. You want to figure out what's changed and just send the pieces that changed. So there's a kind of interesting marriage between diff and patch, which is like a really old technique, and incremental computation and web programming, which is sort of interesting in 2 ways. One, it's like a whole interesting mix of ideas that turn out to work nicely together. And also interesting that the thing you end up with is a surprisingly pleasant thing to actually program with. It has ups and downs. I'd say the biggest advantage is it's pretty easy to understand what your program is supposed to be doing. Understanding the performance and like what, did I put all of the percent maps that, are supposed to make it incremental in the right places and how that works out, that's more subtle. But in the end, it is subtle thinking about the performance, but you have an enormous amount of power, much more than traditional systems for dealing with virtual DOM. So for example, when you want to deal with like enormous sorted tables, there are natural ways of dealing with that inside of this framework. And in the React world, they're like, yeah, we just have some like imperative nasty thing that we don't understand that well that like does all that work on the side. And then we just like, after we get something small enough that we could possibly deal with, we walk forward from there. So it really does, I think, increase the kind of power of the approach in a nice way. And that, I think, is all I got. It's worth saying, if you are interested in this stuff, this is now all open source. We're still actively churning on it. There's IncreDOM is like the little framework that ties all this stuff together, incremental and all the kind of DOM manipulation stuff. IncreMap has all the clever diff and patch-based stuff for dealing with maps, and we have more of this stuff coming out for dealing with other data structures. And this is like the last of a series of blog posts I wrote like back in February, kind of working through these ideas and talking about the kind of background behind it all. So, any final questions?
This kind of said that, so the final conclusion that you still have to do, isn't that coming from the fact that you're trying to generalize that basically you just have values and it can, so the nodes in your graph are general. You're not making special models for saying that for lists, I'm trying to make a different kind of delegation of events when it's going to and when it's not going to. But you try to handle the whole structure.
Right. So I think I would agree with that, but I would call it a virtue rather than a problem, which is to say, what happens is you can take the same kind of trick that was done in a very limited special purpose way for just the virtual DOM, and now you can do it anywhere on any data structure that supports that kind of operation. And this kind of, in some ways, liberates you from the constraints of the kind of traditional way people do virtual DOM optimization, in that you can do totally ordinary functional programming techniques, and you maybe have to get to the point of saying, oh, well, in order to make this part efficient, maybe I have to like go and write some diffing algorithms to make this part efficient. But it gives you a kind of smooth transition where you can write something in a simple all-at-once way, and then go in various places where it needs to be faster and incrementalize it without disturbing the understandability of the logic. In some sense, it takes one shitty problem, which is writing really efficient web UIs, and turns it into two nice problems. One nice problem is writing a simple declaratively described user interface, and the other is doing some clever optimization on the algorithm side. And those problems are kind of both more pleasant and in some sense easier to solve individually, and solving rather than like the kind of mess that you get when you try and do them together.
The level primitive data structures at a lower level. You build a linked list, a dynamic linked list.
So it's worth saying incremental is just a self-adjusting computation library.
So could you not build a map, for example, a map
that is like fundamentally incremental, right? That sort of has it built into it, right? So I think you could, and a lot of the, so incremental comes out of like the academic study of, there's a bunch of papers on what's called self-adjusting computations that came out of CMU, fun work, and they did a lot of stuff like you described, where they kind of integrate these kind of dynamic incremental things into their data structures. But I think the reason I like this mode of programming better is because using incremental sucks, right? Like everywhere where you have to stick this monadic nonsense, it makes everything worse. So it's nice to have a kind of smooth system where you start out, you can be as functional as you want to be, and then you get to, in places where you want, add the incrementality. And the point is you don't have to invent new data structures. Like one of the cool things about all these map-oriented stuff was we had symmetric diffs just like lying around. It was like a function we'd already written. We're like, oh wait, we can take this thing we already wrote and just like glue it together in a very simple way. And after we had to extend incremental sum to make it work, so it wasn't that simple. But I think it gives a happier marriage between traditional functional programming techniques and incremental programming, right? I think that's really the kind of novelty of this. Is like, oh wait, no, we don't have to pick one world or the other. We can smoothly transition between the two.
Have you looked at Abed and Ohm, for example, and how they...
I've looked, yeah.
Maybe something that you can't actually use, because I think what they do is they can do the work of sort of figuring out whether they...
So I think Ohm and React and Elm are basically all making the same trade-off in slightly different ways. Like, I think each and every one of them cannot solve the sorting problem, right? And the sorting problem, for what it's worth, is very easy in our case. We just sort of say, oh, I want a sorted version of the map. Well, I'll just sort of do a transform that like knows how to add something and knows how to remove something. And then I kind of read off the symmetric diff from the input map, and that causes me to do the appropriate set of operations on the output map. And I now, kind of at sensible incremental cost, have a sorted data structure on top of the, a data structure where I kind of change how it was sorted from one to the other. And any of these things, we have like a cursor telling you the identity of things where they are, like they're just hosed. They cannot solve this kind of problem. They're lacking the expressive power to say it. All right, thanks.